This is lesson number 6 for engineering dynamics. In this tutorial we will look at relative motion. So the tutorial contents includes an introduction to relative motion with translating axes, and we'll complete 5 problems. Okay, so what I have here is my xy coordinate axis, and I've also attached the unit vectors I and j at the origin. So the unit vector I points in the x direction and the unit vector j points in the y direction, so you would have seen these before. So I'm going to call this coordinate axis here a stationary frame, and what I mean by that is that this whole axis here is fixed, okay, it doesn't move. Let's say if we wanted to define the position of particle A and particle B inside this stationary frame, we would use these vectors here. So r sub A is the vector position of particle A, and r sub B is the vector position of particle B. And what I can do is attach another coordinate axis onto particle A, which I'm calling y prime and x prime. So the unit vector I points in the direction of x and also points in the direction of x prime. Okay, and likewise j points in the direction of y and in the direction of y prime. So this coordinate axis is what we call the translating axis, because this coordinate axis here, the x prime y prime axis, moves with this particle. So it's attached to that particle. No matter where you put this particle inside this stationary frame, this coordinate axis will move along with it. So we can also define the position of particle B relative to A, okay, and I'm going to call that r sub B slash A, and what that slash means is just relative to, okay, so if you see this, it basically means the position r of particle B relative to particle A. So this is the position of B relative to this particle, and we use this translating coordinate axis here to define the position of particle B relative to A. So we're going to write out the position of particle A and particle B in full vector form. Okay, so the position of particle A has a distance x1 on the x-axis in the I direction and a distance y sub 1 on the y-axis in the j direction. Okay, so if I draw those in, it would look like that. So that's x1 there and that's y1. And if I do the same thing for particle B, so it's got a position x2 on the x-axis in the I direction and a position of y2 on the y-axis in the j direction. If I draw those in, it would look like that. Okay, so there's x2 here and there's y2 there. Okay, so if I find the difference between r sub B and r sub A, I'll get a distance x prime on the x prime axis and a distance y prime on the y prime axis. Okay, so they are here. When you subtract two vectors from each other, you subtract the components in the I direction and the components in the j direction. So if I did x2 minus x1, so x2 minus x1, I'll get x prime. And if I did y2 minus y1, okay, so y2 minus y1, I'll get y prime. And that's there in red. Okay, so then I can write out the position of particle B relative to A like this. So a distance x prime in the I direction and a distance y prime in the j direction. So therefore we can say the position of particle B relative to particle A is x prime in the I direction plus y prime in the j direction. Okay, so it's this. So because we've said the position of particle B relative to particle A is x prime plus y prime, and we already know that r sub B minus r sub A is equal to x prime plus y prime, we can therefore say r sub B minus r sub A equals the position of particle B relative to particle A, and then if I add r sub A to both sides, I'll get this. Okay, so all I did was just add this to both sides to be left with this expression here. And then if I take my time derivative to get velocity, so if I take this expression here and take its time derivative, I'll get this. So r sub B dot equals r sub A dot plus the position of particle B relative to A dot. So I'm going to rewrite that like this. So that is the velocity of particle B equals the velocity of particle A plus the velocity of particle B relative to A. Okay, so that is our relative velocity equation here. And then we take the second time derivative of this expression to get acceleration. So that will give us this here. So 2 dots is telling us 2 time derivatives. And I'm going to rewrite this like that. So the acceleration of particle B equals the acceleration of particle A plus the acceleration of particle B relative to particle A. Okay, so that is our relative acceleration equation here. Whenever we're doing problems, we always take these equations here and write them out in their full vector form. So for this equation, that is its full vector form here. So the position of particle B it's got a distance x2 in the I direction and a distance y2 in the j direction. And for r sub a, we write a distance in the x direction, which is x1 here, plus a distance in the y direction, which is y2 there. And we do the same thing for the relative position as well here. And we do the same thing for velocity, so we'd write velocity like this. Okay, so the particle B would have a velocity in the I direction and a velocity in the j direction, and particle A would also have a velocity in the I direction and a velocity in the j direction, and the relative velocity would have two components in the I direction and the j direction. And it's the same thing as well for acceleration. So make sure you write these down, okay, because for the problem sets we're going to do, we will be using these equations regularly. So this is all there really is to it. So what I've done here is just taken that translating coordinate axis x prime and y prime and put them onto particle B. Okay, so sometimes you might get given situations where they'd swap it around, so you might have to find the position of particle A relative to particle B. Okay, so the relative position is going to be written like this. So the position of particle A relative to particle B, and it's minus there because the position of particle A from B has a distance of minus x prime here and minus y prime. So that's why we've got a minus there. So that means for our relative velocity equation, we're going to have a minus there, and for our relative acceleration equation, we'll have a minus there as well. So again, write that out in its full vector form, which looks like that. And also another thing to be aware of is that you might be required in some situations to draw out a velocity triangle. So if you're given certain bits of information, so let's say for example the angle between the velocity of the particle A and velocity B, you might have to use what's called a velocity triangle. To construct that, you just take the velocity vector for each particle and then you draw in the relative velocity, which would always connect the two. So if I take the velocity of particle B vector there and the velocity of particle A vector here, connect their tails together, the relative velocity would always complete the triangle. Okay, so you would construct that like this. There's the velocity vector for particle A, velocity vector for particle B, and this is the relative velocity. And also be aware that if this coordinate axis here, x prime and y prime, was attached to the particle A, the relative velocity vector here would be pointing in the opposite direction. Okay, so again, make sure you write these down, and it might be worth copying out this diagram just to make sure that you have all the notes you need. Now that we have completed our introduction to relative motion with translating axes, we're now going to complete 5 example problems. So example 1. What is the velocity of car B relative to car A at the instant shown? So let's start off with question 1 here. So there's our relative velocity equation. We write this out in its full vector form like this. So the velocity of car B, we write that in terms of its I and j components. The velocity for car A, we write that out in terms of its I and j components. And the velocity of car B relative to car A, we write that out in terms of its I and j components. So if we look at car A and car B, we can see that car A has a velocity of 4 meters per second in the I direction and nothing in the j direction. And for car B, it has a velocity of 10 meters per second in the I direction and nothing in the j direction. And the relative velocity between the two cars is going to be, even though it's pointing in this direction, this component of the relative velocity is going to be 0, because the distance between the two cars in the j direction doesn't change. Okay, so if you imagine if you was inside this car and there was another car here, and as you're both moving along, the velocity between you in the j direction is going to be 0. Okay, so that means this term is going to go because we have nothing in the j direction for car B. This term is going to go because there's no velocity in the j direction for car A, and this term is going to go because the relative velocity between the two cars in the j direction is going to be 0. Okay, so that term goes too. So then we're just going to be left with this. So what we need to do now is subtract both sides by v sub A to get this. We then substitute our numbers in, so the velocity of car B in the I direction is just going to be 10 meters per second, and the velocity of car A in the I direction is going to be 4 meters per second. So we substitute those numbers in, and we get the relative velocity between the two cars as 6 meters per second, and that is in the I direction. And that is our answer to question 1. So for question 2, what is the acceleration of car B relative to car A? There's our relative acceleration equation. So same thing again as before that we did here. All the components in the j direction are going to go. okay, because there's no acceleration in the j direction for car B, no acceleration in the j direction for car A, and there's no relative acceleration in the j direction because the relative velocity in the j direction between the two cars was 0, which means this term is going to go as well. Okay, so we're just going to get left with this, and we knew the acceleration of car B in the I direction was 3 meters per second squared, and the acceleration of car A in the I direction was 2 meters per second squared. So we want to find the relative acceleration between the two. So subtract A sub A from both sides to get this. Substitute our numbers in. So the acceleration for car B was 3 meters per second squared. For car A it was 2 meters per second squared, which we put here. And the acceleration of car B relative to car A is going to be 1 meters per second squared. And that is the answer to question 2. Okay, so for question 3, what is the velocity of car A relative to car B? So now we're trying to find the velocity of car A relative to car B. So now I've just moved my coordinate axis onto car B like this. So the x prime and y prime axis, I've just moved that from car A to car B. So the relative velocity this time is going to be pointing in this direction, and we've renamed that as v sub A slash B, which means the velocity of car A relative to car B. As we mentioned before, if we was to move the coordinate axis from one particle to another, the relative velocity just becomes negative. So the velocity of car A relative to car B is going to be minus 6 meters per second in the I direction, and the acceleration is going to be minus 1 meters per second squared in the I direction. Okay, so that completes example 1. Example 2. From the perspective of the passengers in car A, the car B appears to be moving away from them at an angle of 50 degrees to the x prime axis. Find the velocity of car B relative to car A and the absolute velocity of car B. So what we can do is construct a velocity triangle out of the velocity vectors for car A and car B, and then we can complete that triangle with the relative velocity of car B relative to car A. So we knew that the angle between the relative velocity vector and the x prime axis was 50 degrees, but because x prime over here is parallel to x over here, the angle between the velocity vector for car A and the relative velocity is going to be 50 degrees. And we were told this angle here was 35 degrees from the x-axis here to the velocity vector for car B. So that's how we got 35 degrees there. Okay, so there's our relative velocity equation. So we write that out in terms of its I and j components for car B, and the I and j components for car A, and the I and j components for the relative velocity as well. So for car B, the velocity vector has a component in the I and j direction. In the j direction, it's going to be VB times cos 35, which will give us its component in the I direction. And the component of this velocity vector in the j direction is going to be VB times sine 35 degrees. Okay, and the velocity vector for car A, v sub A, has no component in the j direction, so that term is going to go. It only has a component in the I direction, and the relative velocity vector here has components in both the I and j direction. So the component of the relative velocity vector in the I direction is going to be minus VB slash A times cos 50 degrees. Okay, it's minus because its component in the I direction is going in this direction, and its component in the j direction is going to be VB slash A times sine 50, and that is going to be positive because it's going in the positive j direction. Okay, so if we write all that in, we get this. So VB times cos 35 degrees in the I direction for car B, and VB times sine 35 degrees in the j direction for car B. And we said the velocity of car A was entirely in the I direction, and we've got 0 in the j direction. And for the relative velocity in the I direction is going to be minus VB slash A times cos 50 degrees plus VB slash A times sine 50 degrees in the j direction, and that is positive because it's going up. Okay, so I'm going to simplify down this term, this term, this term, and this term using my calculator to get this. And I've also substituted the value for the velocity of car A with 10 meters per second because I knew that from the question. Okay, so next what I want to do is collect all the terms in the I direction. So this term here is in the I direction, that term is in the I direction, and this term is in the I direction. So if I put them all together, I'll get this, and then I'll collect all the terms in the j direction, and the terms in the j direction is going to be this term and this term here. Okay, so I'll put them together like that. So you can see here that we've got simultaneous equations that we need to solve. Okay, so we'll solve these simultaneous equations. So I'm going to use the substitution method. There is more than one way to solve simultaneous equation, but I'm going to use the substitution method. Okay, so I'm going to rearrange this equation here for VB, okay, by just dividing both sides by 0.57 to get that, and then simplify that down. So 0.77 divided by 0.57 will give me 1.35. I then substitute VB into this equation here. Okay, so all I did was take VB after I've simplified it down and substituted it into this equation to get this here. Okay, and then simplify this down using my calculator again. So 1.35 times 0.82 will give me 1.11, and then I add this term to this side because I'm trying to get everything with a V sub B slash A onto one side. Okay, so simplified that down and then added this term onto this side, and then simplifying it down even further, and then divide both sides by 1.75 to get the relative velocity as 5.71 meters per second. Okay, so that is the velocity of car B relative to car A. And then to find the absolute velocity, I just take my value for relative velocity here and substitute that into this equation. Okay, so if I do that, I'll get this, and then I'll divide both sides by 0.57 to get this, and then simplify that down in my calculator. VB equals 7.72 meters per second, and that is my absolute velocity for car B. Example 3. Car B travels in a straight line, whereas car A moves on a circular path with a radius of curvature r equals 40 meters. So that is the radius. At the instant shown, what is the velocity and acceleration of car B relative to car A? So we're trying to find the velocity of car B relative to car A. So we have our translating coordinate axis attached to car A, and we want to know the velocity and acceleration of car B as seen from car A. And I've also drawn in my stationary frame, which is the fixed XY coordinate axis. So there's my relative velocity equation here. Again, I'll write this out in terms of its I and j components for each term. So because car A and car B are moving entirely in the j direction at this particular instant, that means this term's going to go, this term's going to go, and this term is also going to go as well. So we'll be left with this. Okay. So then I substitute my values in for the velocity of car B, which was 12 meters per second, and for car A it was 5 meters per second. So I just substitute that into here, and then to find my relative velocity, I just subtract both sides by 5 meters per second to get this, and the relative velocity is going to be 7 meters per second. So the velocity of car B relative to car A is 7 meters per second. So now we're going to find the acceleration. So there is my relative acceleration equation. I'll write that out in terms of its components as well to get this. Okay, so the acceleration of car B in the I direction is going to be its centripetal acceleration, which is just VB squared over R. So that is its centripetal acceleration, which is acting towards the center. So that is going to be positive. And it also has an acceleration of 10 meters per second squared in the tangential direction at this particular point. Because of where the car is, this acceleration is going to be acting in the I direction, and this acceleration is acting tangent to the path. So that means this acceleration is going to be in the j direction. And the acceleration of car A is going to be 0 meters per second squared in the I direction, and it's going to be 4 meters per second squared in the j direction. And the relative acceleration is going to have components in the I and j direction. Okay, so if I substitute VB there with 12 meters per second, that will simplify down to 3.6 meters per second squared. And then what I'll do now is collect all my terms in the I direction. So this term's in the I direction, that's 0 in the I direction here, and this is in the I direction also. So I put them together, and then I collect all my terms in the j direction to get left with this. This term's in the j direction, this term's in the j direction, and this term is in the j direction as well. Okay, so we can see here that the relative acceleration in the I direction is going to be 3.6 meters per second squared, and the relative acceleration in the j direction is going to be 6 meters per second squared. So all I did was just subtract 4 meters per second squared from both sides. Okay, so that is our relative acceleration in the j direction. So I can take these two values, okay, and connect them together and form them into a triangle. So it would look like this. So I've got 6 meters per second squared in the j direction, And then I've got 3.6 meters per second squared in the I direction, and I can construct a triangle out of these two relative velocity vectors, and the resultant relative acceleration is going to be here. So to find that, all I'll do is apply Pythagoras, simplify that down in my calculator, and I get the acceleration of car B relative to car A as 7 meters per second squared. And that is the second answer to this question. Okay, example 4. Car B travels on a circular path with a radius of curvature of r equals 20 meters. So the radius of curvature is 20 meters at a constant velocity, whereas car A moves on a straight path. At the instant shown, what is the velocity and acceleration of car B relative to car A? So what we have is this blue car here, car B, traveling in a circular path at this particular instant, and we've got car A here in red, which is moving to the left with a velocity of 20 meters per second and an acceleration to the left of 3 meters per second squared, so it's increasing in acceleration, and the velocity of car B along the circular path is constant at 15 meters per second. The first thing we want to do is draw our velocity triangle. So what we do is we take the velocity vector for car A. So we start with velocity first. So we take the velocity vector for car A and we draw it here. The velocity vector for car B and we draw it here. Okay, and the angle between them is going to be 50 degrees. Okay, so the angle between the velocity vector, so if you imagine that arrow is drawn here, the angle between that arrow and this horizontal line is going to be 50 degrees. So you can kind of imagine if this angle here was 0 degrees, that this angle would become 90 degrees. And then if you made this angle 90 degrees, this angle would become 0. Okay, so at this particular instant, this angle is 50 degrees. And the velocity of car B relative to car A is drawn here. Okay, so this is how you would draw the velocity triangle. So you would take the velocity vectors for car A and B, and you always join their tails together, like this. Okay, so you always join the tails together. So there's our relative velocity equation. Write that out again in its components, and then we substitute the numbers in. So the velocity for car B is going to be minus 15 meters per second times cos 50 degrees in the I direction, and it's negative because the horizontal component, the I component of velocity, is going to the left, so that means it's going to be negative. And the velocity for car B in the J direction, so the vertical direction, is going to be positive 15 meters per second times sine 50 degrees multiplied by the unit vector J, and we equate that to the velocity of car A, which is minus 20 meters per second, so it's minus because it's going to the left, plus the relative velocity written out in its components. So we simplify all that down. Okay, so I simplified this term and this term down to this. Then I collect my terms in the I direction. So that's going to be this term here, the minus 20 meters per second, and this term here. So I collect them down there, solve for the relative velocity in the I direction, and I get 10.36 meters per second. Collect my terms in the J direction, so this term here, which is 0, and this term, to get this. Solve for the relative velocity in the J direction, and I get 11.49 meters per second, and that is the component of the relative velocity of car B relative to car A in the J direction. So next I'll draw the velocity of car B relative to car A and its components here. Okay, so this was plus from here, and this component here is positive from here. Okay, so if we find out the magnitude, we apply Pythagoras to these two, and we get 15.47 meters per second, and that completes that part of the question. And if we wanted to find what angle the relative velocity makes with the horizontal, we just apply trigonometry, so inverse tan of 11.49 meters per second, which is the opposite, and over 10.36 meters per second, which is the adjacent, which will give us this angle here, okay, which is 47.96 degrees. So because we found this angle, that means it's going to be the same as this angle, because this line here is parallel to this component of the relative velocity. So that means we can say this angle here is also 47.96 degrees. So now we're going to repeat this using the scalar approach. So when we use the scalar approach, we don't have to worry about the direction, so we're just going to use the magnitude of velocities to calculate the relative velocity. Okay, so we're going to use the cosine rule for that. So here's the cosine rule. So for this triangle here, this is the equation for the cosine rule. So you can look this up, okay, and remembering that this angle here that we found, that wasn't originally given, okay. So we're going to be using 50 degrees, which would correspond to beta here, okay. So we substitute the appropriate numbers in. So side A is going to correspond to the relative velocity here. Side B is going to correspond to the velocity of car A, and side C is going to correspond to the velocity of car B. So again, we don't need to worry about the directions. I'll just rearrange that for the relative velocity by just square rooting both sides. Then I'll substitute the values for velocity of car B and car A and the angle beta, which was 50 degrees. Okay, so I'll substitute all that in, simplifying it down in my calculator, and I get 15.47 meters per second, which is the same answer that we got previously. Okay, so you can also clarify this using the sine rule, because now we know this angle, which is going to correspond to alpha, and we know beta here. We know what this side is and this side, and also this side because we just found it here. So you can clarify this using the sine rule if you want extra clarification. So now we need to find the acceleration of car B relative to car A. So there's our relative acceleration formula. So we write that out into its components. And the acceleration of car B is going to be pointing in this direction. So it's the centripetal acceleration, which is pointing towards the center of curvature, which is VB squared over R. So if you're not sure about this equation, refer back to tutorial 3, where we explain this. So this is going to be pointing towards the center because the velocity along the circular path is constant at 15 meters per second. Okay, so we want to find the components of this acceleration here. Okay, and that is going to be the components of the acceleration of car B in the I and J direction. And we know car A is accelerating at 3 meters per second squared to the left. So that means the acceleration is going to be negative here because it's going to the left. So substitute the components of acceleration for car B into here and here with VB squared over R. Okay, so this is going to be negative because the component of this acceleration in the I direction is going to the left. And the J component is also going to be negative because that's going downwards. Okay, so the component of this acceleration in the J direction is going to be negative because it will be acting downwards. So we substitute the acceleration of car A as well with minus 3 meters per second squared. The acceleration of car A in the J direction is 0 because it's going to the left. And we don't know anything for the relative acceleration just yet. So substitute VB with 15 meters per second in here, and substitute R with 20 meters in here and here. So they will simplify down to this, okay? Simplify it down further to get this. Okay, now collect your terms in the I direction, which is this term, and this term. To get that, solve for the acceleration in the I direction, so the relative acceleration, which comes out to be minus 5.62 meters per second squared. Collect the terms in the J direction to get this. Solve for the acceleration in the J direction, and you get minus 7.23 meters per second squared. Okay, and that is in the J direction. Okay, and that is in the J direction. So now I'll draw the relative acceleration here, and then I'll draw its components in the I and J directions. So this is minus 5.62 meters per second squared, and this is minus 7.23 meters per second squared. Okay, find the magnitude by applying Pythagoras to this component and this component, and I get 9.16 meters per second squared. So you can redo this problem using the scalar approach. So you would take the acceleration vector here and here, okay, and use them to construct a similar triangle. This can be repeated using a scalar approach. Okay, so example 5. A boat with a velocity of 4 meters per second in the southeast direction as seen from the fixed observer is on a river with a velocity of 6 meters per second in the east direction. Okay, so this boat is moving in the southeastern direction with a velocity of 4 meters per second, and the river that it's on is flowing 6 meters per second in the eastern direction. What is the magnitude and direction of the velocity of the boat relative to the river? Okay, so we are trying to find the velocity of the boat as seen from the river. Okay, so we are trying to find the velocity of this boat as seen from the river. You can kind of imagine if you was moving along with this river and you was to look out of that boat, what velocity does that appear to be going to you? And that velocity is going to be different compared to if there was a fixed observer down here looking at the boat. We're going to call the velocity of the river VA and the velocity of the boat VB. And we attach our translating coordinate axis onto the river, okay, because we're trying to find the velocity of the boat relative to the river. And if we draw a horizontal line here, okay, we know that the angle between that horizontal line and the velocity vector for boat B is going to be 45 degrees because it's moving in the southeastern direction. So there's our relative velocity equation. So again, write that out in terms of its components. So for the boat B, its velocity in the I direction is going to be 4 meters per second times cos 45 degrees, and that is positive because that component is going in the positive I direction. And its component for the J direction over here, so the J component of this boat's velocity is going to be minus 4 meters per second times sine 45 degrees because that's going towards the negative J direction. And the velocity of the river has no component in the J direction, only in the I direction. Okay, so 6 meters per second in the I direction and 0 meters per second in the J direction. And we are trying to find the relative velocity here, so we don't know any of these values at the moment. So simplify all that down into your calculator and then collect all your terms in the I direction. So this term, and this term to get this. Okay, solve for the velocity of the boat relative to the river in the I direction to get minus 3.17 meters per second. Collect your terms in the J direction. So this term, and it's 0 here, and this term to get this. And this is just going to be minus 2.83 meters per second, okay, because this term is 0. So we get minus 2.83 meters per second in the J direction for the velocity of the boat relative to the river in the J direction. So then we find the magnitude of the relative velocity using Pythagoras, and we get 4.25 meters per second, and that is our answer for the relative velocity. So to find its direction, you just do the relative velocity in the J direction divided by the relative velocity in the I direction, and then do inverse tan of that, and you get 41.76 degrees. And that is the angle it would make with the x-axis. Okay, so if you found this video helpful and you would like to practice some exam style questions, then click onto the link in the video description and you will be taken to the website. Okay, so you copy and paste the link into there and you'll be taken to the home page. So if you click on courses, engineering dynamics, and this lesson was relative motion. Okay, so you got the formula sheet here as well to help you out. So we've got the formula sheet down here, and if you click on relative motion, which was the topic of this video, so relative motion, you've got the same video here. Okay, you don't need to sign in to watch the video. Okay, so you've got this video here. This video is the same video we just watched, and you've got some practice questions to complete here. Okay, so you've got question 6.1, 6.2, and so on. Okay, so you've got questions that you can practice here. Okay, and the answers are shown on the bottom as well. So the answers are all shown here so you can check your work. And this PDF file is also downloadable. So if you click this icon here, you can download this as a PDF. Okay.